In this session, we'll continue the IIR filter design using impulse invariant method technique. So last class we have discussed about the concept of impulse. There are two techniques. The two techniques for IIR filter design. The transformation technique is impulse invariant technique. Impulse invariant method. So all the basic concepts we have derived for the impulse invariant. So the relationship between the analog and digital frequency in impulse invariant method, we derive the formula that is omega is equal to omega t. So this is a relationship between analog and digital frequency in impulse invariant method. Impulse invariant method. And the h of z, the transfer function we derived, h of z is equal to the summation of k equal to 1 to n ck into 1 divided by 1 minus e power minus pk t into z power minus 1. So this also we derived. So these two we have derived in the last session. Now we'll take some problems for the impulse invariant. Consider the first order system function. Consider the first order. What do you mean first order? First order n is denotes the poles. If n is 1, first order. If n is 2, second order. 2 poles. Third order means 3 poles. Fourth order means 4 poles. That's the first order system function. What's the system function? H of z. Okay, so system function here h of s is given, analog filter. So consider the system function h of s is given in the question paper 1 by s plus pi. So what is 1 by s? This is system function, it contains only one pole, s plus pi, only one pole. So it is equal to 1 by s plus a, for example. So you take, so by using impulse invariant method, you take inverse Laplace transformation h of t which is equal to inverse Laplace of h of s. So this is a of s, analog transfer function. So h of t is equal now 1 by s plus a. You know what is h of t? H of t is equal to, so in Laplace inverse of h of s is equal to 1 by s plus a. 1 by s plus a. So we will get, so 1 inverse Laplace of 1 by s plus a, which is equal to e power minus a t. Okay, e power minus a t. So this is h of t. Take z transform of this function. That is a pole. Pa is the pole a here. So what is the take z transform? So what is e? That is p pole. So take z transform. So how to take z transform? Sampling. So that is h of z. What is the formula? 1 by 1 minus e power minus pk into z minus 1. 1 minus e power 1 minus e power minus pk into z minus 1. So sampling period will take, if it is not given, sampling period will take it as 1. So it is equal to, what is the pole? 1 minus e power minus a into z power minus 1, because the pole pk is given as a. So 1 by e power minus a z inverse. So if a is equal to 1, then h of z is equal to 1 divided by e power minus 1. So 1 divided by a is equal to 1, e 0.368. So this e power minus 1. So 0.368 z inverse. So this is the transfer function by using bilinear transformation. Now what are the coefficients? We know that already we have seen the realization of the IIR. How to realize? Realization. This is IIR filter design. IIR filter design. IIR filter. So it's all pole system. All pole system. So numerator polynomials are zeros, denominator polynomial coefficients are poles. So there is a pole, 1 minus of this one. So this is one pole, A. So 0.368 e power minus A is equal to 1. So 0.368 is the alpha and B. So you know AK coefficients, AK and BK, AK coefficients. So AK coefficients are here. So 0.368. So now how to realize the system? You know how to realize the system. How many? So here M and N. So this is M pole zeros and N poles. So N is equal to 1. N is equal to 1. So N, this is N is equal to, order is N is equal to 1. So N is order of the filter. Order N is equal to, this is the order of the filter. Pole, one pole, and you can say this is the order of the filter system. Order of the filter. Order of the filter. So if N is equal to 1, so number of poles is 1. So the order of the system is first order system. Okay. So the number of poles, so 1. So now what is the delay element is required for to realize this realization of IIR filter? Already we discussed, no? So relay in a direct form 2. You can realize by using direct form 2. Direct form 2 realization. So in the direct form 2 realization, the memories, the delay elements are, so the delay elements, number of delay elements is equal to number of delay elements. How do you find? So the maximum of M comma N. So the N is equal to 1 here. So only one delay element is required to realize this system. So this is Z inverse. So left hand side, as I told, the pole system, all pole system. What is the pole? Minus 1 minus of, okay, actually 1 minus 0.368. You can write this one 1 minus of minus of 0.368 Z inverse, because the formula is 1 minus. So minus of, so what is the coefficient now? Is A coefficient in A coefficient is equal to 0.36. So what is the coefficient here? A1 is equal to 0.368. So 0.368. So 0.368. This is the coefficient. So this is your x of z. This is your y of z. So how to realize a system? Understand? So for the given, so this is example for the first order system. First order system is the poles. Okay, this is a first order system, S plus A. 1 by S plus A. This is 1 by S plus the poles. So you have to take inverse for step 1 to take inverse Laplace transformation. Then second step, you take Z transformation. Then third one, realize the system. Find out the number of poles and realize the system. Hardware realization. Okay, third step, find the coefficients. Then this is the implementation. Similarly, we take one more example. Second problem. H of S is given S plus 1 divided by S plus 3 into S plus 5. So apply the partial fraction method. So H of S, so you can write A by S plus 3 plus B by S plus 5. So how do you find the partial coefficients? A is equal to S plus 1 divided by, that is where S is equal to minus 3, where S is equal to minus 3. Okay, so S is equal to minus 3. So A is equal to S plus 1 divided by, so if you want to simplify this one, S plus 3 will be cancelled. So S plus 5 only will be there. So what is A value? So minus 3 plus 1 minus 3 plus 5, which is equal to minus 2 by plus 2, which is equal to minus 1. So this is your A coefficient, the partial fraction coefficients A. Similarly, you find B. So what is B value? B is equal to s plus 1 by s plus 3, where s is equal to minus 5. So minus 5 plus 1 by minus 5 plus 3 minus 4 by minus 2, which is equal to 2. So b is equal to 2. So b is equal to 2. So this is where b, the partial coefficients. Now h of s can be written as minus 1 by s plus 3 and plus 2 by s plus 5. So now take, this is an unlock transfer function. Now take, okay, inverse Laplace transformation using impulse invariant method. So for impulse invariant method, take inverse Laplace. So h of t can be written as, so this will be minus 1, the coefficient is minus 1 into e power 1 by s plus a, which is equal to e power minus a, that is e power minus 1 plus e power minus at, you can write. So e power minus 3t plus the coefficient 2 into e power minus 5t. Take z transform. So this is h of t. Take z transform. Take z transform. So h of z is equal to, so how you can write this one? So 2 by, we can write 2 by, so directly we know the impulse invariant method, 1 minus, what is the formula? 1 minus 1 by 1 minus e power minus pk into z power minus 1. Take z transform of e power minus pit, so we will get 1 by 1 minus, so 2 by 1 minus e power minus 5, e power minus 5 into z inverse pk. What is the pk here? So there is a e power minus 5 into z power minus 1 plus, that is, sorry, that is a plus minus 1 divided by 1 minus e power minus 3 into z power minus 1, z power minus 1. So now simplify, 2 by 1 minus e power minus 5 will be 0.006 z inverse plus minus 1 divided by 1 minus e power minus 3 will be 0.049, point 049 z inverse. So now how do you realize the system? So this system can be realized separately. This is a cascade section you can do. First, x of is, so 2 by, so for this you take it separately. H of z you can draw, this is h1 of z and this is h2 of z. Okay, so this can be realized. So one delay element here, one delay element separately you can do, or you can combine and you can realize that from 2. So z power minus 1. So the coefficients, the poles are 1 minus of, so plus 0.006. This is x of z. Okay, and the other, the zeros are 2 is y of z, and so you can realize in a parallel parallel system. So the other, the h1 of z, h2 of z, this is h2 of z. What are the coefficient of this one? So one delay element, z inverse, so the coefficients are 1. So poles are here. What are the poles for the second one? So second one is point 0.049, 1 minus of plus, so plus 0.49 and minus 1, zeros are minus 1, okay. This is 1 plus 0.49 poles, so this will be connected to x of z. It's a parallel FA system. Okay, this is y of z. How to realize a system? Okay, similarly, we can solve one more problem. This is a parallel affair. Another problem will take h of s is equal to problem 3. Third problem, 2 by s plus 1 into s plus 2. So h of s can be written as a by s plus 1 into plus b by s plus 2. So what is the a coefficients? So a coefficients 2 by s is equal to 2 by s plus 2 in where s is equal to minus 1. So you can substitute 2 by minus 1 plus 2. So 2. Similarly for b value, it is equal to 2 by s plus 1 where s equal to minus 2. So 2 by minus 2 plus 1, so which is equal to minus 2. So a is equal to 2 and b is equal to minus 2. So now you substitute. So h of s is equal to 2 by s plus 1 plus minus 2 by s plus 2. Take inverse Laplace transformation h of t. So impulse inversion method. H of t is equal to 2 into, this will be, you can write 2 into e power 2 into e power minus t, since it's a 1 minus t, minus 2 into e power minus 2t. Then take z transformation. Take z transformation. Take z transformation. So h of z equal to 2 divided by, so you can write 1 minus in impulse invariant. This is impulse invariant method. So you can write h of z e power minus at. So transformation 1 divided by e power minus 1 into z minus 1 plus minus 2 divided by 1 minus e power minus 2 into z minus 1. So now take common terms. So 1 minus e power minus 1 into z minus 1 into 1 minus e power minus 2 into z minus 1, 2 into 1 minus e power minus 2 z minus 1 plus this is a minus 2 into 1 minus e power minus 1 into z minus 1. So simplify, which is equal to 2 minus 2 into e power minus 2 z minus 1 minus 2 minus plus 2 into e power minus 1 z minus 1 divided by a plus b into a minus b. So this into this 1 minus e power minus 1 z minus 1 minus e power minus 2 into z minus 1 and minus plus e power minus 3 into z minus 2. So now we can the numerator term, you find out the e power minus 2 value, e power minus 2 value, e power minus 1 value. Okay, you will get, simplify, finally will get 0.4651 z minus 1 divided by 1 minus, simplify and substitute the values for minus 4, minus 2, minus 3. So 1 minus 0.502 z inverse plus 0.049 z minus 2. This is your h of z. Now what is m value here? M value is 1, n value is 2, 2 poles. So the order of the system is second order system. This is a second order system. 2 poles. This is 2 poles. So how to realize a system? 2 poles. So 2 direct form 2 realization. Direct form 2 realization. So in the 2 delay elements, the 2 poles. So the 2 delay elements are required. 2 delay elements, unit delay. So 2 delay elements, how do you denote? So Z inverse, the other unit delay element, Z inverse. So you should not do delay elements, you should not put Z minus 2, this wrong. So Z minus 1 and Z minus 1. So on the left hand side, the coefficients are, so what are the poles? So what are the poles? The coefficients A1 and A2. A1 is equal to, this you write 1 minus of 0.502 minus 0, that is z minus 1 minus 0.049 okay, z minus 2. So what is a, this is a1 coefficient, this is a2 coefficients. So a1 and a2 plus 0.502, 0.502, the second a2 coefficients minus 0.049. So second order system. So these are all pole first. Okay. IIR system, all pole is first. So this will be 1. This is uh, x of z. So now the zeros are, numerator term zeros are 1 0 at 0.4651. 1 0 at here, 1 0 at 0.4651. So this zeros. So this is y of z. So this is a realization of this transfer function in that form, two structure, or you can say it's a canonical form. So we can conclude in this session. So there is not, okay, only two elements. So we can conclude the last session, the concept of impulse invariant method. So this session discuss about some of the problems using impulse invariant method. So take more problems from Process and Opening and Nagurkani. You can refer the exercise problems, and more practice is required to solve any problems in the examination. Okay, thank you.